Good morning, everyone. Hope that your week is going pretty good so far. We're going to be looking today at lesson 30.18, which deals with a lot of qualitative material. We're going to be looking at the third model of the atom, the Rutherford model of the atom, and we're also going to be talking about different types of spectra. And everything that we learned today is setting the stage for the lesson that we're going to be covering on Friday, which is dealing with the Bohr model of the atom. And this lesson can be found on page 12 of the current lesson handout. So in 1911, just over 100 years ago, Ernest Rutherford performed a series of experiments which we now refer to as alpha scattering experiments. What he did was he took a very, very thin piece of gold. Gold is a very malleable metal. You can pound it down to an incredibly thin layer. And he fired a bunch of alpha particles at the gold. And his idea here is that based on how the alpha particles interact with the gold, it tells him something about the atoms that make up the gold. Just so you know, we've talked about this before, but it's been quite a long time. An alpha particle is the same as a helium nucleus. The phrase helium-4 nucleus may not mean much to you, but in the latter part of this unit, we'll talk about what that 4 means in detail. Basically, it means there's 4 particles that make up the helium nucleus. There are 2 protons and 2 neutrons. And these particles are emitted by naturally radioactive radium. Later on in this unit as well, we're going to be looking at natural radioactivity. And one type of radiation is called alpha radiation. So that's what these particles are. So by observing how the alpha particles interacted with the gold, and gold is made up of atoms, Rutherford was able to deduce certain properties of the atomic structure. What he discovered in the experiment is most of the alpha particles, probably about 95% of them, went through the gold with very little deflection. So what you're looking at now, we have a zinc sulfide screen that is wrapped around the apparatus, and basically a zinc sulfide screen is a chemically treated screen that will light up when an alpha particle hits there. So literally what this experiment involves is you sitting and staring at this screen and counting how many tiny flashes of light you see and in which places you see them. So he discovered that most of the alpha particles went through with very little deflection. The conclusion he's going to draw based on that observation is that most of an atom is empty space. About 5% of them, which is almost all of the remaining alpha particles, were deflected significantly, maybe through angles of 30 or 40 or 50 or 60 degrees. But very, very few alpha particles, it was less than 1%, were scattered through very large angles, which means that some of the alpha particles hit something and bounced back. But since very few of them had that encounter, whatever they were hitting was rare in terms of the structure of an atom. And based on all of this, Rutherford was able to come up with a visual picture of the atom. And we call it now the nuclear model of the atom. And the reason it's called the nuclear model of the atom is because buried deep inside of it is a nucleus. Now this diagram you're looking at is not drawn to scale. It's not even close. The nucleus is exceedingly tiny. And the electrons as well on this diagram are way too big. They should be drawn smaller. But that doesn't matter. Here are the properties of the nuclear model of the atom. The majority of the mass of the atom is in the nucleus, and it's in a very, very, very tiny region of space. It's the nucleus that odd alpha particle strikes that causes the alpha particle to bounce backwards. And the reason why very, very few of the alpha particles bounce backwards is because that nucleus is such a tiny target. The likelihood of an alpha particle hitting it is pretty slim. We now know that inside of the nucleus there are further subatomic particles called protons and neutrons, and we know that the electrons orbit the nucleus at very, very large distances. So there's a lot of nothingness to the atom. There's a lot of space between the nucleus and the electrons. By the way, since atoms are neutral, the number of electrons in the atom is the same as the number of protons in the atom. So we went from Dalton's model of the atom in this unit so far, which says that atoms are like a tiny billiard ball, but impossible to break. Very childlike in its simplicity, and totally wrong. Thomson then, after electrons were discovered, came up with this model of the atom. And the physics theories say that if atoms were actually like this, some kind of globule of positiveness, whatever that is, some sphere of positive fluid with the electrons embedded within it, there's no way that alpha particles could be deflected as much as they are in Rutherford's scattering experiment. The reason why the alpha particles are deflected is they are encountering something that has a lot of charge and a lot of mass. And Thomson's model of the atom takes all of the mass and all of the charge of the atom and spreads it out. It dilutes it over a large space. So when alpha particles encounter something with the physical structure of the Thomson model, the alpha particles will essentially just go straight through, and they will never really be deflected. So now we have the Rutherford model. And I like this view better rather than the three-dimensional view. The three-dimensional view is more accurate, but this gives you an idea of why we can call it the planetary model. This is like a bunch of planets in orbit around a star, like our sun. It is an expectation in this course that you understand how to go from one model of the atom to the other in terms of what happened historically to cause that change to take place. So the discovery of electrons led to Dalton's model of the atom being modified to Thomson's model of the atom, and alpha scattering experiments resulted in the need to take Thomson's model of the atom and further modify it by creating the nuclear model of the atom. That's the first part of this lesson. Just understanding basically what the Rutherford scattering experiment is about and understanding how we go from one model of the atom to the next model of the atom. The next thing that I would like to talk about today is the main problem with Rutherford's model of the atom. Rutherford's model of the atom by no means is the final story about atomic structure. There are a number of serious problems with the idea of electrons in orbit around nuclei. But the biggest problem is that Rutherford's model of the atom cannot explain what we call atomic spectra. And before I talk about why Rutherford's model of the atom is a bad model of the atom in terms of atomic spectra, and in fact, even before I talk about atomic spectra, we're going to have to talk about what a spectrum is. First of all, the word spectra is plural of spectrum. So you have one spectrum, but you have two spectra, or three spectra. What a spectrum is when you take the light coming from some source and you spread it out so that you can see all of the colors. A perfect example of this is that if you were to take a look at sunlight, you would never look directly at the sun, but if you take a look at sunlight, you shine sunlight on a piece of paper, basically the light is white. But when you spread out the light coming from the sun, you discover that it contains a lot of colors. We call those colors the colors of the rainbow. And the rainbow is considered a spectrum. Well, it turns out there's different ways that you can observe a spectrum. You have to use what's called a spectroscope or a spectrometer, and basically what you do is you shine the light that you want to spread out through a diffraction grating. And we know that long wavelengths of light diffract and interfere at larger angles, so what you end up getting is the colors being spread out. And if the light to be analyzed had every single color, then what you would see over on the right-hand side would be two rainbows, two complete spectra that contained every color. So you could use a diffraction grating spectrometer. And that's what we would be using in class if we were in class. You could also use what's called a prism spectrometer, because it turns out that when you shine light through a refractive medium, like a prism, short wavelengths refract less, so you end up getting the light spread out based on the wavelengths. And again, if that light source ended up containing every color of the rainbow, then on the right-hand side on the screen, you would see every color of the rainbow. So now what I want to do is talk about the three different types of spectra. The first type of spectrum is called a continuous spectrum. And that's what a continuous spectrum looks like. It's sometimes called the rainbow of visible light. You do need to know that in order to produce a continuous spectrum, you need a solid glowing object. So what we are looking at here is a light bulb, and this is not an LED light bulb. It is not a halogen light bulb. It's what's called a filament light bulb. And in North America, they're not even manufacturing these anymore. But in a filament light bulb, you have a piece of wire that is heated up by passing an electric current through it. And the light coming off of that, it turns out that when you pass that light through a diffraction grating, you will get continuous spectra. You will get a rainbow on one side and a rainbow on the other side. And if we were in class right now, I would turn on one of these light bulbs and I would give every student a diffraction grating, and we would look through the diffraction grating and observe a continuous spectrum on the left and a continuous spectrum on the right. The best I could do here is I took a picture by putting a diffraction grating in between my iPhone's camera lens and a bright light source. So that bright white in the center of the picture you're looking at right now is the glowing filament. I'm using a special type of bulb that has a vertical filament. It's a vertical piece of wire that's glowing. And you can see on the left and the right, you get a continuous spectrum. The spectra have these kind of bubbles to them, but that's only because the filament, and I'm going to draw the filament on here using black, the filament is being supported by some wires so the filament doesn't wobble around. And those wires that are supporting the filament are blocking some of the light, and that's why you get these kind of bubbles happening in what you're looking at. But anyway, that's a continuous spectrum, and it's produced by a hot, glowing solid. The second type of spectrum that's produced is called an emission spectrum, or a bright line spectrum. Now, I don't know what the quality of this video is going to be like, but you should definitely be able to see a red line of light here, a greenish line of light here. There is a blue line of light, which I hope my capturing software will pick up. There is also a violet line of light over here, which I can just barely see right now. So I doubt very much that it will be captured by my capturing software. But this is called an emission spectrum, and it's produced by taking a gas and heating it up. So, for example, when we take a look at a hydrogen spectrum and we heat up hydrogen and you observe the light through a diffraction grating, you see only these four particular wavelengths. Now, if we were in class, I would turn on a hot hydrogen gas sample and we would look at this through a diffraction grating. So this is what's called a gas discharge tube. It's a glass tube that's filled with a gas, and when I turn the power on, there's about 10,000 volts of potential difference applied to the gas, and the gas glows. This is what you might call a neon tube, although technically it would only be a neon tube if the gas in it were neon. But when you see in a place like Las Vegas, or you see in a nightclub, all of these glowing tubes, they're working on the basic principle that we're talking about here. I love the fact that it says, do not put fingers in sockets when turned on. If I do turn it on, now this is not hydrogen. I believe this is helium. But you can see when I take a picture of this through a diffraction grating, you can see I get a whole bunch of these images on the left and the right. Starting on the left-hand side, I see a red line, I see an orange line, I see a yellow line, I see a green line, a purplish line, a violet line. So I'm getting all of these different lines. And that is what a bright line spectrum looks like. So inside of this tube is a glowing gas. The third type of spectrum is the opposite. It's in fact the exact opposite to an emission spectrum or a bright line spectrum. And what you do in this situation is you take a glowing solid, which is the light bulb you're looking at, and it, don't forget that glowing solid is emitting every color of the rainbow. If I go back and take a look at that glowing solid, it produced this spectrum. So this light bulb is producing every wavelength of visible light, everything from 400 nanometers to 700 nanometers. But if the light that's leaving that light bulb is allowed to pass through a cool gas, so the light is leaving the light bulb, but it's passing through a gas that's cool, which means it's at a low temperature. And what happens is that continuous spectrum of light that's hitting the cool gas goes through the gas, but the gas removes some wavelengths, some colors. So what you're dealing with here are missing wavelengths. We're missing a wavelength here, we're missing one here, and one here. And by the way, and this is the most significant part of what we're talking about in terms of getting you ready for the next lesson, the wavelengths that are missing in the absorption spectrum or the dark line spectrum are exactly the same as the wavelengths that are emitted in the bright line spectrum. So if this is the dark line spectrum for hydrogen, it's missing those 4 lines. This is the bright line spectrum for hydrogen. It has those 4 lines. And this is Rutherford's problem, essentially, is why does hydrogen emit only 4 wavelengths of light? Or why does hydrogen absorb only 4 wavelengths of light? There is no question in anybody's mind that a hydrogen atom contains a single proton with a single electron in orbit. There aren't even any neutrons in the simplest form of hydrogen. It contains 2 pieces, an electron and a proton. So if Rutherford is going to claim that what's going on in hydrogen is you have an electron in a circular orbit around a proton, then he'd better be able to explain how those 2 particles work together to produce those 4 colors of light. And that essentially is where we're going to pick up on Friday. Before I just finish this off, I do want to show you what you're looking at on the board here is the bright line spectrum for hydrogen. You can see 4 visible lines. So basically, everybody, hydrogen has the ability to produce very specific wavelengths of light, and hydrogen has the ability to absorb certain wavelengths of light. The wavelengths of light that are absorbed are the wavelengths that are missing in the dark line spectrum. The wavelengths of light that hydrogen emits are the wavelengths that are there in the bright line spectrum. And by the way, every atom in the universe has its own unique spectrum. What this means is that if I am looking at light from a distant star through a telescope, and I pass that light through a diffraction grating and see this pattern of lines on the left and the right, then I know it's helium. If I want to know if there is carbon on a star, then I can observe what the spectrum is for carbon here on Earth. So I've selected carbon, and it has those lines. Now I know what the bright line spectrum for carbon looks like, and the dark line spectrum. But if I go looking through a telescope at a star and I see those lines, then I know that there's carbon on the star. So it's a very useful tool in terms of astronomy. That's it for the lesson. You don't have any assignment attached to this. I'm just going through this material to set the stage for what we're going to be doing on Friday, because if I tried to pack today's material in with Friday's material, I think it just might be too much. So, Rutherford's model of the atom is an improvement of the Thomson model of the atom because of the results of alpha scattering experiments. And you need to know what the Rutherford model looks like. But then you need to know that the big flaw in Rutherford's model is it cannot explain even something as simple as the hydrogen atom in terms of line spectra. And that's it. So have a great rest of the day. You don't have anything that you need to work on for physics for next time, and we will talk to you soon. Take care.